My name is Kozyrev, and I work for NVIDIA, and I work on the Kinetics NIC family, and mostly I focus on the hardware offloading. And I'm going to present you with the two talks about the Flow API and how we do the hardware offloading in our NIC. And the first topic today is the packet type matching. And it's advertised as the faster way to steer the traffic inside the NIC. And let's start with the agenda. So I will give you the brief overview of the Flow API. And I will talk about how it does the matching and how it performs the actions there, and why is it not always optimal there, and how we can improve things. And by the end of this topic, I would like your opinion of the Flow API as well, and see if you have any ideas to improve things as well. So let's start with the generic Flow API overview. As I mentioned, the idea is to offload as many actions as possible from the CPU to the NIC, to the smart NIC, because with the current situation, the throughput is climbing very fast, and it's hard for the CPU, for the applications to keep up with the packet processing. So the idea, the whole approach is to push as many things as we can to the smart NIC itself and let the hardware do the work instead of the application doing that. And Flow API is generally very simple. You have two API calls. One of them is flow create, when you offload the rules to the hardware, and flow destroy to remove the flow from the hardware. And the general structure of the flow rule is the following. There are multiple other details about that, such as attributes. Is it going to be on the NIC domain, on the TX domain, on the FDB domain? And the priority, you can stack the flow rules in the hardware according to your needs, to your application needs, and assign the priorities to them. But the most crucial parts and the most important ones is the pattern. Pattern which says that what packets are we expecting to arrive at this rule. And it can be Ethernet, the protocols, the metadata, the port ID, and so on and so on. And the second part is actions. Action list says what are we going to do with this packet. There are multiple ways to manipulate the packet. We can encapsulate it, decapsulate, encrypt, modify some headers, and assign tags, forward it to some port, do the RSS to get to this application. And the list goes on and goes on. So let's see. Let's focus on the pattern here. In this topic, I would like to focus on the pattern. And as I mentioned, we can match on the protocol data, so we can IP addresses, destination UDP ports, and so on and so on. And we can also match on the ports, the originating ports, on the metadata that we insert into the MBUF, and so on and so on. So, but the main design of the pattern structure is, if you have the protocol layer structure, you have to match them, and you have to put the protocols one by one according to the OCI layout. And why is it not optimal? So today we support many combinations in the DPDK. There are layer 2, layer 3, and layer 4 headers. And there are up to 16 layer 2 headers, up to 16 layer 3 headers, and up to 16 layer 4 headers. And that means that to track every packet, to offload every packet there, you have to have 4K rules in your hardware table. And if you add the inner outer, the encapsulation, it's 4K multiplied by 4K, it's unmanageable. But let's not go to the extremes. There are simple cases. For example, we have the combination of IPv4, IPv6, and TCP/UDP case in the simple application plus some encapsulation, for example, VXLAN. And again, in the inner headers, you have the IPv4, IPv6, and in the outer IPv4, IPv6, and TCP/UDP. So that gives us about 16 flow rules, which is not so bad. But how we manage these flow rules in the tables inside the hardware? The table is linear, so whenever you receive the packet on the RX queue, you traverse the table and see for the match, see for the exact match for all the protocols that you stacked inside it. And there is a performance implication of that. There is a small performance degradation when you miss the rule in the table. It's small, but still it's noticeable. And if you have many rules inserted, it's getting worse and worse. And that's why when you design the application, what we always suggest to our customers and our users, and that we would like to prioritize the most important, the crucial traffic first, and you put and organize the hardware flow tables that way, that you hit the first most important packet in the beginning of the tables, and try to handle the rest of the cases somewhere close to the end of the tables. So on this table, you can see that I missed around 10 times when I arrived to the final rule that matches my traffic, for example. And how to deal with that? How to optimize this table? Because we still need a way to handle all this combination. For example, we would like to match the inner UDP only, but there are multiple combinations. So you see I have to select IPv4, IPv6 cases, UDP, TCP cases. And the same is true for the inner headers as well. IPv4, IPv6, and finally I got the UDP. So with the current approach in the DPDK, there is a wildcard. It's type any that can bypass multiple protocol layers in the RT flow API. And for example, you say, I don't care what the protocol at this place in the stack of the protocols is. I just need to skip it and proceed to the next layer. But there are a few caveats with this approach. It's working, but it's, first of all, you need to understand in the application when you program the hardware flows, you need to understand is it L2 tunnel or L3 tunnel. So you have to know how many layers you need to skip. And the second one is that you have no way of match the absence of protocol. For example, if you want to handle packets that has no encapsulation, no inner UDP case, there is no way you can do that with the any type. And that's why recently we introduced in the Milanox driver the new packet type matching item that follows closely the structure from the MBUF. So every application developer already familiar with that type, and it has all the information about the layer 2, 3, and 4 types, and tunnel protocols, and inner L2, L3, and L4 types as well. So from the user point of view, it's very easy to adopt it, and whenever you get the packet, you get all the information, you save the packet type, and you can quickly apply it to the hardware and say, from now on, the work on this type of packets will be handled in the hardware. So from this structure, you can see that it's easy. You can just specify the inner L3 and inner L4 type as a UDP, and that's it. You only get the inner UDP packets into your flow. And you decide then what to do with this packet. You can send it to the application or do the manipulation and send and forward it to the different port. Yeah, so the benefits of this flow rule float is the following. I mentioned that it's part of the MBUF. It's easy to program the flow with this. And there are masks in the definition of the packet type in the DPDK, so you can easily pick and program the combination of the protocols. For example, you can combine the outer and the inner protocols and prioritize the traffic you want exactly. And it works on both layer 2 and layer 3 tunnels. You just need to specify the inner header type, and the hardware will do the job just fine. And the last point is that also we can mask the absence of protocol with this type. So whenever you set the mask, for example, you want to specify the inner L3 mask, and then in the flow rule you set the as 0, and that means that you're gonna receive all the packets that don't have the L3 inner header, and that's it. And basically that's the whole my presentation. We support this in the Mellanox driver from 23.11, and we encourage other drivers to implement the Flow API items as well, just to get the benefit to the users. And the question is to you after the forum, do you have any other inefficiencies than in the Flow API that could benefit the community as well, and we will be gladly to review them and try to implement. Thank you.
John Carney, Excite Labs. In practice, do you see like applications like require like a large number of patterns that then you search sequentially, or or like do you have an idea of some applications require 50 patterns or 5 patterns?
Yeah, the table that I showed you in this particular example, it's a basically customer use case.
It's a real use case?
Yeah, that's a real use case. They basically need to sort out all the outer combinations, and they just need to process the inner combinations first. And they experience some kind of inefficiencies. They say that data output is not what they expect it to be, and that's why we engaged with them, and we showed them how to optimize the flow tables inside the hardware, and that's why we came with this idea.
And this reduced to just a single pattern?
Yes. If you say, I would like to match all the inner UDP packets, it's just single pattern. So you have the hit on instant once you get the right packet. And again, we tell the customers and the users that you have to prioritize the rules which corresponds to the most common traffic you're going to receive. That's why you get the best performance.